In a car lift, compressed air exerts a force F, capital F you write, exerts a force F on a small piston, having a radius of, 5.0 centimeter. This pressure is transmitted to a second piston of radius 15 centimeter. If the mass of the car to be lifted is 1350 kg. Calculate F. 1350. Calculate F. What is the pressure necessary? To accomplish this task? Given G is to be taken as 9.8 meter per second square. This task, accomplish this task, question mark. Then in the bracket write down G, acceleration due to gravity, G equals 9.8 meter per second square. You cannot take 10, that's what they mean. So we write down what are the things given. Car lift compressed air exerts a force F1 on a small piston. Say I write F1 as F1, we write it as F1 only. On a small piston of radius R1 we call, that is 5.0 centimeter. Then this pressure is transmitted onto the second piston of radius R2 we call. R2 is 15 centimeter. If the mass of the car is to be lifted, that means mass M2, mass of the car 50 kg. Calculate F2, the force required. What is the pressure necessary to accomplish this? P to be calculated. How we start solving this? Say first of all, you are given with R1 and R2. So A1 and A2 are given. We write the formula. F1 by A1 equals F2 by A2 according to Pascal's law. Substitute everything. What you require is F2. F2 is A2 by A1 F1. A2 pi R1 square by pi R2 square. Pi R2 square by pi R1 square into F1 is F1 only. So now this goes, we are substitute for R2 and R1, 15 by 5. There's no need to convert because centimeter get cancelled into F1. So how much it is? 3 square 9F. Write down this, very simple. 9F1 alwa? 9F1. F1 is, okay, that's nice, very simple. 1.5 10 raised to 3, 1500 newtons. We'll see. First, we write down this. F2 is 9F1. F2 is 9, F1. Just write down this. If you have finished writing, we continue with the things. We are asked to calculate F1 only, not F2. We substitute everything. Observe carefully. F1 is F2 by 9. F2 is how much? 1350 into G, 9.8. That is the force to be lifted. Divided by 9. How much it should be? Approximately, that is 4,470 or so, as it is given here. It is 1,470 Newton. Approximately, you can say 1.5 kilonewton, 1.5 thousand Newton. 1.5, that is 1,500 1,500 Newton. So what is the next thing asked? Is to calculate the pressure. What is that we read? What is the pressure necessary to accomplish this? You can calculate by F2 by A2 or F1 by A1 because both are same. Can do it by anyone. In the textbook, they have done it by F1 by A1. We do it by F2 by A2. We'll get the same thing. So pressure is F2 by A2. F2 is 1350, 9.8. A2 is by R2. R2 is how much? 1.9 10 raised to 5. We'll see. R2 is 15. Now it should be converted into meter because all are in meters. There's no correlation of cancellation. You put everything there and I'll get the final thing. What is the final answer which you get there? Get me the answer. Calculate it quickly. 1.9 into 10 raised to 5 you will get. Final answer for this problem, pressure is 1.9 10 raised to 5 Pascal. Pascal. So that is the answer what we need to get. With this, we proceed on to very new concept, what we come across in day-to-day life also. The final answer I have written it here, 1.9 10 raised to 5 Pascal. Add up these things. So, okay. With these ideas, now we proceed on to other things. Say, till now, we learned fluids at rest. That means when they are at rest, what is the effect? Now, from this point onwards, we start with what is their effect when they are moving. In fact, everywhere, wind is blowing, wind is moving. In our body, blood is moving. So, to convey water to our houses from the water tank or somewhere, the water will flow through the pipe. All these things. And in fact, fluid dynamics, what we want to learn. In fact, can you believe, on that day I told you, behind understanding the star's growth, mechanics means statics plus dynamics. Dynamics means where the fluid flows are at the base of understanding star birth growth and death. That's very important. And there are some unsolved questions even today. What you may take and solve that. For that, you may get good prizes, Nobel prizes. In fluid mechanics, there are some such problems that I will tell you later on. Now, say we just imagine a pipe of this shape, one side bigger and one side smaller. Now we imagine the fluid is flowing, say water is flowing, or any fluid for that matter. Fluid is flowing. Then, if we can measure the velocity of the particles, fluid particles, portions of the fluid, on their path, say, I take a portion, a point P there. And we imagine consecutively we have some particles there, what we name as 1, 2, 3, 4. And I take another point also. Say, we take Q there. Now, as one passes through this point in the fluid, one means it's the part of a liquid only. We are considering the portions of the fluid 1, 2, 3, 4 in the flow. Once the particle 1 or the portion 1 enters P, we imagine its velocity is like this and it is 5 meters per second. And once that particle, if it passes through this, its velocity in this direction, I'm using word velocity. Velocity means it contains both direction as well as magnitude. Remember that. That's why you must always be careful what word is used. Velocity or speed. That's very important. So now, velocity is used. Here, we call it as Vp and this as Vq. I can take it as 10 meters per second, some value. Now, the second particle 2 comes all the way to point P. Can you believe? Whatever may be the velocity here, once it touches the point P, that is, once it is at P, its velocity automatically becomes 5 meters per second. And once it moves on to Q, automatically it becomes 10 meters per second. If there's another point in the path where it passes, say R, there also its velocity becomes same. Say it may be 11 meters per second. So again it acquires 11 meters per second. Then once the third particle comes to P, it acquires 5. Comes to Q, it acquires 10, including direction. And comes to R, it again, say 11 or something like that. That means when a flow of fluid is there, there's one particular type of flow. That's what we are discussing. In that flow, what we call a steady flow, strictly speaking, this type of flow is called as steady flow or streamline flow that we are learning now. What do we mean by that? We try to explain. Already we learned it. We try to put it in an elegant manner. So it's a type of flow in which the particles which passes through a given point acquire same velocity at that point as its, say, preceding particle, which has passed, say, 1 is preceding to second, second is preceding to 3, 3 is preceding to 4. That means first which passes, that is the first one. As it acquires, second one also which passes through that. That means that type of flow is called as steady flow or streamline. Let me repeat it. Steady flow or streamline flow is the one in which the velocity of the particles passing through a particular point is always constant. In the next point, it may be different, but it is constant there. In the next point, it may be different, but it is constant. Observe here. P, all the particles which passes through P have 5 meters per second at P. All the particles which passes through Q will have same velocity 10 meters per second. Which passes through R will have 11. That means that is what we mean by steady flow. So again, just we repeat, steady flow means it is a flow in which the particles passing through a given point in the fluid have the same velocity at that point. All the particles which passes through that point have the same velocity. That point may be anywhere in the flow, not only particular thing. It may be anywhere. That's what we call a steady flow or streamline flow. Let me repeat it and then proceed. A steady flow is a type of flow in which the velocity of the particle at a given point, velocity of the particles, we say, at the given point is same when they pass through the point. All the particles which pass through that, they have same velocity with this. Now, what does this indicate? Can somebody think of it? Observe, I am saying velocity. This sentence, even though beautifully said with so many examples, it is indicating an inherent, very important idea regarding the flow. What does it? Can you think of? Can you think of? Okay. As the fluid moves like this, as each particle has to follow the preceding particle, then each particle has a particular path. It goes on moving. So both direction and magnitude to be maintained. That's why in this type of steady flow, nobody can expect the particle to come back. It just moves forward, just like soldiers march fast, one behind the other, no question of coming back. In a long road, if they start march fasting, they go one behind the other with same speed. But here, its speed is not same at all points, it is different, but at particular point, it is constant for all the particles which pass through. Likewise, one behind the other, it goes on more. Do you want an example for this? It's a beautiful example, what you can try. You take incense stick, you take incense stick and ignite it. Ignite it. You know, the smoke starts coming out of it. Is the incense stick, smoke starts coming out of it. Just observe the smoke. Don't go very near to that because your breath may disturb that. So it starts rising like this and then it gets scattered there. So in the beginning, when it leaves the incense stick, it is smoothly flowing like this. All the smoke, we can see how they move. But after some distance, it gets scattered like this. It moves. In fact, here is the example for steady flow or streamline flow. And another one opposite to this is, what is that? Can somebody tell me? Opposite to steady flow, turbulent flow. Turbulent. No conditions valid. Water, liquid or fluid can move in any direction. No conditions. So turbulent, we write. Turbulent. Do you know, in Caris, there is one canal by the side of musical fountain, what is called as Vishesharaya Canal. In fact, in that canal, once water rushes out of the dam, it is turbulent because there are some, to check the speed of the water, they made some obstructions inside the channel. That's why water becomes very turbulent. That churns like that. Once you visit that, you just look into that channel, the water flow. That's a beautiful example for, say, turbulent flow. And also, in the incense stick example, as all the smoke moves in a beautiful manner up to certain extent. After that, it gets scattered. So that certain extent, that part is example for steady flow, according to this it passes. But after that is example for turbulent. Why I said don't go near to that, because once we go near to this, our breath may create small wind there, and that may disturb the smoke itself. So we cannot see that. Just keep the thing at little bit distance and look at that. This smoke will beautifully rises up to that without any disturbance. After that, it gets disturbed. So that is about steady and streamline flow. And moreover, just now we said, once there is a steady flow, there's no question of turning back. It continuously, just like soldiers, one follows the other, one behind the other. All the fluid parts move one behind the other, and they come out of the pipe. They come out of the pipe. They come out of the pipe. But observe, I'll tell you one thing. Even today, apart from streamline motion, if the fluid comes out of a pipe, no equation is written for that coming out. That is coming out of the pipe, what we call as ejection of the fluid from the pipe is not written. No equation is written. And that's even today unsolved problem because it's not easy to write down. It's very complex and even today it's not written. So as you just put the message back, I cannot read that. Please put it back. Okay, now we observe. So once you know streamline and turbulent, what can we do to increase the distance of steady flowing incense sticks? You have to keep the thing very calm. No question of, say, some small disturbances in the air in the room. Then you can create. So as is asking me this idea, say what to do to increase the steady flow distance in the smoke of the incense stick. That is not so much easier. It is hardly around 2 to 3 centimeters or maximum 5 to 6 centimeters it can. After that it get disturbed because the air is somewhat, even though we don't feel, air particles are moving. They are moving randomly. That's why it is not so easy. ಇರುತ್ತೆ ಬಟ್ ಇಲ್ಲಿ ಏನಾಗುತ್ತೆ ಏನಿದ್ದಕ್ಕೆ ಇದಕ್ಕೆ ಎನರ್ಜಿ ಜಾಸ್ತಿ ಇರುತ್ತೆ. The energy given to the particles, smoke particles by the, say, some hard object is there, no? That ash or something like that. That makes it to move possible. But once it reaches, by that time it loses some energy and it may get disturbed. Or it may get some energy also, more energy also by the surrounding air. Therefore it gets disturbed. That is most probably the major idea is it gets the energy, not losing the energy. It gets the energy, thereby it gets disturbed by some or the other means. Because this room, in this room or where you are sitting, lot of air is there. One cannot predict where the disturbance is there. It's not so easy to predict. They are very complex systems. But fortunate thing is we can understand the air by a very simple idea. Not only air, fluids by simple idea like this. But steady flow is physically possible. We can achieve that as in this case. But how long we can take that fume as a steady flow, that decides. That is decided by many, many factors. But to make it, you have to keep the surroundings as much quite calm as possible. That may also. There are many. Observe carefully. Prajwal is asking me, thickness of the incense stick, will it matter? Maybe. These are the ideas, how we think or how Swaz thinks. So these are the questions. If you start investigating by keeping an incense stick, becomes a research project. That's what the scientists do, apart from theoreticians. Theoreticians means they go on thinking on the practical ideas given by the others. But practical ideas, what you are thinking, if you put them into experiment and write your results, that itself is the analysis, or what that itself is the research work. But that is to be done, my dear friends. That curiosity should be there. Now Swaz can try how to increase the length of the steady flow in the incense stick. Whenever you get bored, just try to do some experiments to keep it as long as around 10 to 15 centimeters or 16 centimeters, like that. It is quite possible. You may find some new results also by that. That's what is required for intel competition or anywhere. That's the idea. Okay, with that, once we learn these things, as there's no question of change in the path of the fluid particles, one behind the other, they move continuously. Now I can write an equation like this. Just observe. What is the mass of the fluid entering at this point? Say at this end, we call it as end 1. Should be equal to the mass of the fluid which is leaving at the end 2. Can you get this point? How much mass enters here per unit time? Should be same as mass entering out of this So mass is leaving out of this pipe at the same time. Say here, what I mean is 1 liter of fluid, say water you can take, is entering per minute. Then, because of the steady flow, 1 liter of water should come out per minute here also. Can you guess why? Because there's no question of turning, there is no question of stoppage, nothing. One behind the other, they move slowly, as with their velocity, it may be slow, it may be fast. Therefore, all the particles enter here with the same, actually, so much particles should go out there, because otherwise there may be a crowding. If some, say, 10 particles enter here in 1 second. If only 8 particles come out, what will happen then? 2 may retain. Then streamline flow or steady flow is not possible, because somewhere they are getting accumulated. That's not possible. One behind the other, they have to move. That's why in the streamline flow, no question of stopping, no question of turning back, what we call as rotational, that we think of later on. Rotational fluids, they are there. Rotational motion for the fluids, that we think of, whirlpools. Sudi, that's a rotational motion. And then rotation, they are there. Let's not bother about that. That most probably in the next session or in the coming sessions we'll learn. Just observe carefully now. As no particle can turn back or no particle can reduce the speed and stay there, these are all impossible in this steady flow. Therefore, my idea is 1 liter or 1 kg can take. Mass of the, what is that, Adurta? You said intake a large part? I don't know. Just put it back. They will vary, so it may be accelerated, but it cannot turn back. ಆಗೋಕ್ ಸಾಧ್ಯ ಇಲ್ಲ, ಯಾಕಂದ್ರೆ ಇಲ್ಲಿಂದ ಇಲ್ಲಿ ಬರ್ತಾ ಇರ್ಬೇಕಲ್ಲ, ಈಚೆ ಮಧ್ಯದಲ್ಲಿ ಎಲ್ಲೂ ನಿಂತ್ಕೊಳಂಗೆ ಇಲ್ವಲ್ಲ. ಇವೊಂದು ದೇ ಮೇ ಬಿ ಆಕ್ಸಲರೇಟೆಡ್, ಇಲ್ಲಿ ಆಕ್ಸಲರೇಟ್ ಆಗೋದು ಇಲ್ಲಿಂದ ಇಲ್ಲಿಗೆ ಬೇರೆ ಬೇರೆ ಆಗುತ್ತೆ. Prajwal is asking a very good question. Can they be accelerated? Definitely there is acceleration of the particles, or deceleration also may be there. But idea is this condition to be satisfied. At suitable points when they move, they continuously acquire that velocity. Say in the diagram shown again, put it back. I cannot read so quickly there. I'm talking to Prajwal and others here. So okay, we go proceed, and if you get the doubt, I'll just put it back. Observe, if we write the equation for these two masses in a diagram in the going, hey, again I missed it. Just put it back. In the diagram in going area is large, there water comes back. No, it's not possible. It will not come back. It simply goes out. Where the larger area, smaller area, it is irrespective. It simply goes out. Loss of energy due to the friction, sir, that is, we are not thinking. Beautiful thing. So as you asked, we are thinking an ideal fluid. Ideal fluid means there's no friction between the particles of the fluid. That we eliminated. And it is incompressible also we are taking. In all these situations only this is possible. Streamline flow. But it should be incompressible. It should be an ideal fluid, means there is no viscous force, there's no frictional force between the layers of the fluid or something like that. That's not possible. That we think of later on. We go on introducing the, say, complications little later. But before that, observe carefully. By this, that means mass of water entering at one point is equal to, in the given time, is equal to mass of water leaving at that point, at the other point in the given time, and in the same time. I can take in any intermediary thing also, not going or coming. At that point, say 3, in somewhere inside the pipe. Even there also, 1 liter per minute definitely passes, 100%. That means rate of flow of mass of the liquid or fluid always remains same. But by using or by writing equation for this, we'll arrive at a beautiful equation. What we name it little later. Just also. We write the equation now. How we write? I just rub this off and then we'll write if it is required. Say at any 2 points we take point 1, point 2. Mass of what? Fluid entering is equal to mass of fluid per unit time or in the given time. At 1 is equal to mass of fluid passing through 2 at the given same time. Say I write mass of fluid passing through given point. Say we take 1 passing through given area if you want, given through given area in given time. Given area means the tube area there. Given time should be equal to given time at 1, say at 1 part. Same thing at 2 in the same interval of time. So how to write the mass in terms of density and all those things? So we just think of it. I write 1 part there to understand. This is of area A1 and the fluid enters here at velocity V. For example, we take V at this point V. It maintained up to some certain distance, small distance. Then how to write the mass of the fluid entering here in time delta t? Can somebody get me? Mass of the time entering into that pipe at that point or passing through that point in time delta t. How to write? Mass is how to write in terms of density? Density into volume. We write here rho into V1 I write down. V1 is the volume. Is equal to rho into V2 we write. Rho cancel. But how to write V1 and V2 at 2 points, any 2 points? How to write? What is V1? Volume. Area into length. Pi r square h. Area into length. So A1 into length, how to write? Say in delta t time, all the particles entered, they come out to this part. Then this is the distance covered by that in delta t time. What is that distance? Can somebody tell me? Nice. It is right, Surya. It is velocity into time. Velocity is x by t. So distance is x equals v into t. So distance is v delta t. V delta t. So similarly, v2 can also be written. We write first v1. How to write? Rho in say rho v cancel v1 only. V1 delta t volume. Agreed? Area is A1 and this length is V delta t. Area into length is volume. On this side, what should we write? Some area, this area A2 and the now as it is large area, small distance may be covered. Therefore, this is again V2 delta t, here V1 delta t. Therefore, A2 V2 delta t. Cancel delta t. What you get? Why it is possible? Because no particle will stand at given position. It continuously moves. So can you give a name for this equation? Can you give a name for this equation? Try. Why this is happening? Because of the continuation of the particles movement. Nowhere they stop, nowhere they turn. Therefore, can you choose a name for this? Equation of continuity. Say, because of the continuous motion of the particles, it is happening. Otherwise, it is impossible. Continuous motion not only as they require, as they wanted, it is governed by one behind the other, just like soldiers march fast. Therefore, A1 V1 equals A2 V2. You take many points there, you can simply write A1 V1, A2 V2. Need not be out of the pipe or not, need not be at the end of the pipe. Even at the middle, you can write at any point, A4, B4, any number of points. Always this quantity, the product of area into velocity is always constant. This is what we call as the equation of continuity. In the exam, board exam, we were asked to say, derive this equation of continuity. Derive the equation of continuity. Write down. Write down the question there. Write down the question. Derive equation of continuity. 3 marks question. Derive equation of continuity. Derive equation of continuity. Most probably today also time limit is not there for us. So I just go through this. By the time you conclude this, then actually if you write up this, write the answer for this question, there I conclude after this. So I write down derive expression. What is it? Continuity equation. What you have? The derive equation of continuity. But observe what to write as a preamble sentence. First write down the figure like that, what one streamline flow figure, and then show 2 areas, A1, V1, where A2, V2 velocity, like that. If you want, I'll write down that once again in a little bit clear manner. It may be bigger area, smaller area. This you call as A1, the velocity of the flow, V1 here. Here the velocity of flow, V2, A2 area, like this. The flow is this way, flow is this way. Then you call this as 1 and this as 2. Portion 2. Then you write down this equation. Like this. First line you have to write. Consider a fluid. Consider a fluid. Area of cross section more and speed low. It may be. It should be, because the product should remain same. Therefore, it should be. If area is more, speed is less. If area is small, speed is more. That we think of later on. And the meaning of this is also same thing, equation of continuity. But there you write down a sentence in the beginning. Consider a fluid flowing in the streamlined manner in a pipe as shown. Only one line. Consider a fluid flowing in a pipe in the streamlined manner as shown. In the streamlined manner as shown. As shown. You write down this simple figure. Where A1, A2 are the areas of cross section on 1 and 2. V1 and V2 are the velocities of the thing at 1 and 2. Velocities of the fluid at 1 and 2. Mass of fluid passing through given area in given time. At means at 1. Is equal to same thing you write on at 2. And also listen one thing, from Monday or next Thursday, we start physical classes here only, because anyhow government has given the permission for the colleges also. We are here around 18 or 17, so why to bother? We can go for it. I will inform you later on. Most probably not Monday, from next Thursday also. Monday as usual, this type of classes only, Monday, Tuesday, Wednesday, that we think of. So just write down these things. Here V1 and V2 are observed. There are 2 V1 and V2. This you write down capital V1, capital V2, this small V1. You must be able to practice, or you must practice to write small lowercase v is bigger V, lowercase u, bigger U. They are little bit important because they may confuse you when you write it in a same manner. Say volume I use always capital V, for say velocity we use small v. Capital V means we write like this. And for velocity, I usually write lowercase v in a slightly stylish manner like this. And there's one more thing to confuse us, but what we are not using. If you write like this, what is this? This is a Greek alphabet, it is nu, nu, nu. What is used for frequency? That will learn later on. So there are very similar. And also there is one more like this. It is called as gamma. Greek alphabet again. These three are confusing, especially this is not so much, but this gets confused with the R. These two are very important. And this capital V, you have to write down properly. Okay? With these things now, if you have finished this derivation,